Here's a beautiful geometry puzzle. We have an isosceles triangle ABC where AB equals AC, and the apex angle is just 20 degrees. Now pick a point P alongside AC so that AP equals BC. The question is, what is angle PBC? Pause and think about it. Let's start with what we know. Since AB equals AC, this is isosceles. Remember from geometry class, the base angles of an isosceles triangle are always equal. 180 minus 20 divided by 2 gives us 80 degrees at both B and C. Now the key constraint, AP equals BC. How do we use that? The sine rule. It bridges angles and sides. In any triangle, each side over the sine of its opposite angle gives the same ratio. Set AB equals AC equals 1 and apply it. BC comes out as sine 20 over sine 80. Now let's zoom into the smaller triangle PBC. We know angle PCB is 80 degrees. Let's call the angle we're after X. Then angle BPC must be 100 minus X, since the three angles always sum to 180. Here's the strategy. Apply the sine rule again, this time inside triangle PBC. This links our unknown angle X to the known sides. And what is PC? Since P sits on AC, PC equals the full length minus AP. And since AP equals BC, PC is simply 1 minus BC. So we need PC over BC. Watch the algebra unfold. We substitute our expression for BC, and the fraction simplifies to sine 80 minus sine 20, all over sine 20. Now here's where a beautiful identity kicks in. Remember the sum to product formula from trig class? Sine A minus sine B equals 2 cosine of their average times sine of their half difference. Let's apply it. Sine 80 minus sine 20 becomes 2 cosine 50 times sine 30. And sine 30 is just 1/2. One of those facts worth memorizing. So this whole expression collapses to cosine 50 over sine 20. Remarkably clean. Let me step back and explain the game plan. Your first instinct might be to draw auxiliary lines or try pure angle chasing. Those can work, but they require clever constructions that are hard to discover. The sine rule approach is different. It's systematic. It turns geometry into algebra. We used it once in the big triangle to find BC, and again in the smaller triangle to set up our equation. No magic tricks needed. I want you to feel like you could have discovered this. The clue was the equal length condition. That's your signal to reach for the sine rule. Now let's solve our equation. The right side has cosine 50 over sine 20. Here's a nice connection. Cosine 50 is the same as sine 40. Why? Because 50 and 40 are complementary. They add to 90. And sine 40 is a double angle. 2 sine 20 cosine 20. See the common factor? Sine 20 appears top and bottom. Cancel it, and we're left with just 2 cosine 20. So clean. Let's verify. Test x equals 70. Sine 30 is 1/2, so we get 2 sine 70. And 2 cosine 20 is 2 sine 70. It checks out perfectly. And there it is. Angle PBC equals 70 degrees. Does this make sense? Think about it. P is close to vertex A because AP equals BC, which is the short side. So the line BP cuts a steep angle from the base. 70 out of 80 degrees, that feels exactly right for a point high up on side AC. So the answer is 70 degrees. The key insight, the sine rule turns geometric constraints into algebra, and the sum to product identity reveals hidden simplicity. This kind of angle chasing appears in surveying, where engineers calculate precise angles between distant landmarks using exactly these relationships. If you enjoyed this, like and subscribe for more.